Good morning, everyone. Good afternoon and good evening. Thank you for coming to this session. And I am Djillali Benouar. I am professor of earthquake engineering and disaster risk management at the University of Science and Technology in Algiers. And I'm a member of PERIPERI U for 15 years now. And I am also the chairperson of the African Science and Technology Advisory Group. I am participating in many expert groups of the UNDRR to try to brainstorm what can be done, because the situation is not as good as we expected. You know, maybe some of you know what's happening in Algiers or northern of Algeria about these forest fires, where maybe 70 people, they lost their lives. And they, of course, many villages now, they are completely demolished by fire. They lost people, they lost animals, they lost everything. Then I think it's very important to take seriously one more time this disaster risk reduction and implementation to Sendai. Yeah. Yes, then today, really it's like, it's the following the presentation of Mr. Kai from the AUCDRR unit on African indigenous perspectives on disaster risk climate change nexus, that I got the idea, and I said, oh, maybe he has done for disaster risk climate, I can do that for earthquakes in Algiers, since Algiers in or whole Algeria or North Africa is in the border of the two tectonic plates, the African tectonic plates and the Euro-Asian tectonic plates. And said maybe it's a good to show our friends in Africa what is earthquake and how people before us, they protected themselves. I'm not sure they did it voluntarily or involuntarily. Then we try to find out how these people, they have done that. Then today, I am very pleased to present the indigenous, you know, people. The word indigenous people, they don't like it in Africa, because indigenous, like autochthone, that's a term from colonization. That was big discussion during the global platform about this word. I prefer traditional knowledge, because now we are all autochthone. We are the real people in Africa. Then the indigenous knowledge in earthquake risk reduction to protect the Casbah of Algiers. The Casbah of Algiers, or the old nuclei now of Algiers, we thought, you know, it was always studied by architects, just about the arts, about how people, sociology, how people were living inside, how the society is living. But this time, like 10 years ago, engineers at the University of Science and Technology, Faculty of Civil Engineering, we said, oh, why this Casbah is still standing after all these destructive earthquakes? Maybe there are some things that protected the Casbah. How come it's still until now? And people are coming, tourists and everything are coming to visit it. And we tried to make a PhD for that, trying to read the techniques that we believe they are abnormal to normal construction. Now I'm gonna share the screen with you. Mm-hmm. Yeah. Oh, this is the Casbah. This is the Casbah of Algiers here. The Algiers is made of hills, and this is the Casbah of Algiers, and it is the harbor, the harbor of the port of Algiers. Then the Casbah, really, it was built in the 16th century. You know, the Ottomans, they arrived in Algiers in 1520s, and they started to build the Casbah on the ruins of the Roman city called Icosium. Then there was a city, small city, Roman city, Icosium. When the Ottomans came in 1520, they built on the ruins of this city. Then this is the Algiers, the Casbah, how it looks now. Oh, here, this is the Casbah, the old nuclear of Algiers. And this is now, but the Casbah, original Casbah was up to the water, up to the harbor. But the French people, they destroyed all the lower Casbah. They destroyed all of it, and they built, as we see now, European buildings. The Casbah started in this boulevard here, going up. Still, we can see it. Then this is the Casbah we can see. This is up here, the citadel. The citadel where the Ottomans were fighting, from where the Ottomans were fighting conquerors coming from the sea. You know, this is the upper point in the Casbah. Now we tried after, you know, Algiers, or the Casbah, was destroyed by an earthquake in 1716. 1716 was destroyed. And it is said that the Ottomans, when they came from Turkey, they built the Casbah with villa and gardens, what we call, maybe it's an importation of culture to Algeria. An importation, they imported their culture with villa and gardens. But when the 1716 earthquake hits Algiers, all these villas were destroyed. And the governor is called Bey at that time, the governor of the city, you know, imposed earthquake seismic resistant technique after the earthquake. And they were implemented by all the people. Even if you couldn't find the paper from the archives, but they said there is like a seismic building code at that time to rebuild back better the Casbah after the 1716 imported like techniques from the Ottomans, where we can find these techniques in Turkey, in Greece, in Syria, in all these Mediterranean, in Egypt, all these Mediterranean, Mediterranean countries, they have this type of traditional measures. What is good in this, when we started to read the Casbah, it's not like nowadays, we just design for earthquakes, just the building itself. It will behave as one building. But for the traditional measures, we have the urban scale, which is new for us. We have the architectural scale, and we have the structural scale, meaning the house itself. In the urban scale, how they did their measures, how they implemented these measures in the blocks, in the urban scale. There are blocks, not only individual buildings, but blocks of buildings, varying number of houses. In each block, there is a certain number of houses, individualized by communication streets, very narrow street, which surround them. These make each block containing several houses, reacting independently from the others during the shaking. Then each block is behaving during earthquake, meaning the energy released by earthquakes is not absorbed by one building, but it's absorbed by a block, which may absorb a lot of energy from that released by the earthquake. This is in urban scale. The houses, how are the houses? The houses they're not separated. They are semi-detached, overlapping. They're overlapping one another and leaning against each other, forming a compact, homogeneous unit. And this is good for the energy that make the shaking, then the whole block. Then from the house to the house, the energy is transmitted. Then it's absorbed by the blocks or the houses. Now, between the blocks, always in urban scale, between the blocks, we have what we call the Sabbat. The Sabbat. The Sabbat is a number of streets which are covered by galleries, on top of which the houses extend from each side. The galleries are up the galleries, they are covered by houses, and those creating roofed passageway. This can be flat with wooden locks incorporated or vaults built out of the stone and bricks. See, then all the blocks are linked together by these galleries, what we call the sabbats, bigger streets. Then the energy is transferred to the whole city at that time by this sabbat. But we have also, in the urban scale, we have what we call discharging arches. Discharging arches, which are in the urban scale, and as I use it also for energy transfer from one block to the other. Then the chain of transfer goes from building to the block, and from block to another block to the other building. You see, then it's like transfer the risk. Everybody is participating in absorbing the energy released by the earthquakes. Then the urban framework, number of arches built out of stones or bricks, allow the transfer of horizontal loads or lateral loads generated by earthquake to the ground by the vertical component. Then the force is lateral, but it's transferred to the soil through the vertical component. That this is the way we use discharging arches. Even now we use them in bridges, in many houses, in buildings, to transfer the lateral loads to lateral loads. It may be wind, it may be earthquakes, to the ground. Then construction are not isolated. What is good in urban scale, which we don't have here, we don't have now. That construction are not isolated elements, but compact, dynamic blocks. Compact, dynamic blocks. Then the dynamic of the blocks, according to the energy, will behave accordingly to the energy released by the earthquake. And you can see here the gallery and the arch. And you can see even on the arch here there is houses, and to make a small gallery with a very narrow street. This is the vaults. I show this to show a typical vault in the Casbah of Algiers, in the streets or as a foundation, because most of the Casbah is built on these vaults. Now, in reading the construction, going further deeper in this, we have seen, like a resume of urban scale. Now we go to others, what they have done, what we have found, and we try to explain why they put this according to our knowledge of dynamics of structure, modern dynamic of structure today. With the construction technique were unfortunately, I will say unfortunately, facilitated by the state of degradation. It means we can see everything in the walls, we can see in the foundation, we can see these abnormal things we found in their construction. Then state of degradation, which is predominant now in the minor heritage, because they are trying to make a reinforcement of this building. Look at the structure of masonry construction. This is divided into 4 parts. We try to, in the reading, to try to divide these structures. The first one is the vertical structure, the load-bearing walls and arches. This is the first vertical. what they have done inside. The second is the horizontal structure. It's like floors. What is in particular in floors and roofs? The third thing is the different crossing. How they protected their angles. We know today that during a shaking of earthquakes, the angle of the house, of the building, are very vulnerable. They are fragile. What they have done. We can see the different crossing, like doors, windows, stairs, and we can see the architectural elements, the overhangs, like the balconies, how they have done for the balconies. We will see that. We can see now the architectural scale, typology of the houses. What we have found that most of the houses have central patio, as you can see it in the axonometry view here, which is in black. This is the patios of the houses. Most of them have a central patio of square form. Square is the word, square form, around which the rooms are distributed 2 or 3 levels, no more. Then the rooms, the patio, square form, and the house, and the rooms are distributed to around this patio. Shape of the house, or shape of the houses, I would say. All the houses, they have square form. Why square form? How they knew that square form is good? You know, the shape of the house, square, is being the most earthquake resistance structure. Nowadays, we know that, you know, the circle one, like the cylinder, or the house, a symmetric house with like a square, is the most earthquake resistant design. We know that. In both directions, you have no torsion. If you have like a rectangle, you will have a torsion to and you will have destruction. Then down here you can see the axonometry view of a block. This is a block, how it's done in the Casbah. This is the description of the structure. As I said, the vertical structure, the horizontal structure, the different crossing, and the architectural element overhangs. This is what we found. We tried to start with the walls in the structural scale. Why these walls have resisted? How come? There's no steel inside. There is no concrete. Then we found that there are links of the walls. All the walls are linked one to another by alternative crossing of cedar. It's called tuya, and the tuya was brought from a forest here in south of Algiers, about 50 kilometers, and it's still there. Then they linked to another by alternate crossing of cedar tuya wood logs, consolidating the angles. You can see on the pictures here on the right. This is the wood logs, and every 50 centimeters you have to find here and up the wood logs. You can see here also the wood logs. All the angles, you know, this is load-bearing walls, large, big, and you can see here the wood logs. Then what is good, which we have found, that these wood logs from tuya were well distributed on the height of the wall. It's about 50 centimeters. And cedar wood logs were about 2 meters long, incorporated in the wall. Why they have done that? We try to explain by modern dynamic of structure, because now we understand. Now maybe you can see me. This is shears. The earthquake will create shear and will deform the wall. But when we have two materials, we have the wood incorporated in the brick wall, we have this the displacement between the wall and the wood. When you have displacement, it means absorbing energy. Which energy? The energy of released by earthquakes. And this energy is absorbed by this wood and will reduce the earthquake damage. We reduce the damage. This is, when we put it on the shaking table, this is what we found, a wall like built with a stone without wood logs, and the stone and the wall with stones, with the wood logs. Then you see that the wall with the wood logs is it's better. Now we have seen these load-bearing walls, but inside, to divide the rooms, we have the partition walls. The partition walls are well connected to the main walls, all again by wood logs. Then we have the load-bearing walls, the main walls, and you have the partition walls also. You can see here, shearing walls, wood logs. Here, wood logs, equidistant up to the floor. And this technique, you know, this is like putting the structure together. All the structure is together, all the walls are linked, making it like a block. It's like a block. Now, we go to, just give examples, we go to floors. Floors. The floors, we found that floors are built by superposition of two layers of, like you see here, here, the woods, but two layers of cedar wood logs inserted in the walls, load-bearing, rigid diaphragm, rigid. When we ask the question, why two layers of cedar? Why two layers? What is in between? What is in between? What we found in between is that this space between the two layers is filled up with earth and stones. Why? Why they make it so heavy? Because now we found in modern dynamic of structure as we design for earthquakes, we need a rigid diaphragm, which is the floor, which should be rigid. It should be rigid. Like these people, they know that they should have a rigid diaphragm. How to make it? They make it two layers of wood logs, and in between they filled it with earth or stones or everything. They made like a rigid diaphragm. Now in modern dynamics, we say it's like an assumption. It's like an assumption that the floor is not deformable. It's infinitely rigid. Why? Because when you have the lateral load generated by the earthquake, we think that the lateral load should be beared or equilibrated only by the columns. Then the floor should be infinitely rigid. It explains why they put these two layers of cedars, and in between you have the earth and the filling of that. This is very, very good idea. I don't know how they knew that at that time. Maybe by experience. Another experience we found. Look, the corbellings, like balconies. There are many balconies, you can see here in this picture, or up in the picture. Then the frontal balcony overhanging, which is very bad for earthquakes, because it will balance and fall down. But how these people, they built it? The frontal balcony overhanging and supported by cedar or tuya wood logs, forming an angle with the bearing. See, forming an angle here in the picture. We have them here also. We couldn't understand why they did that. They knew that these balconies are very bad for earthquakes. But when we try to read this picture here you have, we made it in details, try to see each point of these oblique wood logs. We found this. Look at these. Look. Here at the bottom, it's fixed. It's fixed. Look at the top. Free. Free. If it wasn't free here, the balcony won't resist. Won't resist. It's gonna be like a solid thing that will destroy the balcony and even the buildings. And even the buildings, because this wood is inside the roof, the floor. Then if it wasn't free, then all these, they are free on the top and fixed in the bottom. When you have, now we understand why. And this is the way we do it. Because when you have earthquakes, you have two horizontal components, east-west and north-south, horizontal, and one vertical. One vertical. When you have the vertical component of the earthquake, you have this part of the building will go up and down, up and down. Then this one will go up. It will have a free displacement. When you say displacement, you said absorption of energy released by the earthquake. Then everything is, all these disaster risk, earthquake risk techniques are based on energy, how to absorb energy from the urban scale to the architectural to the structural. See, and this made this balcony resist and they are still up to now. We can see these buildings still alive because of this technique, easy technique, but it's not easy to think about them when they do not exist. Now this is again structural scale. We have tried to read or to study the openings. The openings, you know, the windows and the wall and the doors. The windows are all, first of all, their placement, where they are. They are never placed close to the angle. They are inside. Because the window itself, it's empty. It's a zone of fragility of the building. Then they put it far away from the other fragility zone, the angles. Then the doors, same thing for the doors. And more than that, framing. More than that, wooden framing is found around the opening, doors and windows. Then to reinforce the strength of the openings, because they are fragile, we found that for each window and each door, there is a frame, a wooden frame, to make this zone, fragile zone, more resistant. This is one of the technique. The windows and doors frames are also traditionally reinforced with big stones or timber, lintel, aimed at promoting enough resistance to bending, because they're in bending stresses. If the windows are not very large like now, they are small, but they are bending, then they do that, you know, by stones or by wood. Sometimes you have arcs in some bigger windows. Then for the materials, did they use the concrete? Did they use steel? No. They use lime. The building materials, lime mortar, the fat lime. Then we have the slaked quick lime. This is a mixed to a small extent with the earth, gave the mortar of the wall. This is the mortar they used. Arranged in joints between bricks of thickness. The thickness is equal to the brick. You can see in the picture, up in the picture, then the mortar is as big as the brick. We have also the slaked lime mixed with sand and other elements such as charcoal powder and oil, gave the mortar plaster or plaster. This is to show that the building material is a part of earthquake resistant technique, is a part of it. We have the structural and urban and architectural, but we have also the material. And we have the fat lime like you see here, in low addition to the earth, and then lined in the framework and the formwork, gave rammed earth, which appears as a load-bearing wall. This is then like the bricks with the fat line. Wall in some houses of the Casbah. The rammed earth was used mainly for the construction of the element of defense, like citadel. Like citadel, we found this type of bricks with rammed earth. Then this is the. Now we can see the just to show you the building materials. I said what they have done with it. You can see here the bricks to make the arches here. You can see this chimney of the bricks also. There is no steel, wood, brick, and lime. That's all. Here, same thing. This is the citadel where the people were fighting for the sea, for people coming from the sea. We have here the famous vault. You also can see the arch, how they are, and how they are reinforced here, because they transfer the lateral load to vertical to the soil, and this is how they done it here. Same, all the load, up like bridges, like arcing bridges. They have all the like suspended bridges. They have all the load transmitted to the soil by the arcs. Now, there is another thing, what we found. How can we understand that? Why? Something happened here. How these people, they put, you can see here, wood logs in this small part between two different parts of the same elements. This is the elements. Here it can be seen clearly. You can see here, now, because it's easy now, it's rigid. But here is flexible. So look at the slenderness of these. And here it's rigid. Two different rigidity. One is flexible, it can move easy. One is rigid, it doesn't move easily. But when we have that, even now in modern technology or dynamics, if you have one building and two different rigidity, it's going to have big problem. Here, when there is a shaking, this part will move slower than this part. This part will displace larger. Then it will be a big difference here. This is a fragile zone of these techniques. Fragile zone. What to do? Innovation. Without higher technology, just thinking from the wood, from a local material, tuya, cedar. These people, they brought it and they put it here. They put it here. When there is a shaking, this part will move slower. This part down here, since it's flexible, less rigid, it will move more. But in moving, the difference of the displacement between this part and this part will make displacement of the wood logs. What I said, displacement meaning absorption of energy. The energy always released by the earthquake, and this has avoided or reduced really the earthquake damage by putting these wood logs in this part, the most fragile zone of this type of structure. You can see it here, and you can see it here, also here. You can see here the wood logs, even here. Then the Casbah is full of these techniques. We could understand it looking at that for the first time, and as an engineer, of course, about the shaking of earthquakes. Said, why that? Then you start to study, and you find this. Now we can see this is picture to show the columns here with the doors. reinforcement of columns, because this is opening in the bearing walls, and it becomes dangerous, it becomes fragile. And you can see the patio here. All the houses of the Casbah are like that. A patio, and the rooms are around it. And this is a square form. See here. Here, this picture, you can see here, tria in this part. See here. Then still, you can see that now in these big small houses were, still can see that. Then, and this is to transfer the earthquake loads from one side to another column. Now, just to finish, this is to finish. I start with the left picture. Because there's a degradation and a lot of works going on, we found something we couldn't understand. We look at it, but it was already made in 1980 in New Zealand. What we call seismic base isolation, and we thought that the New Zealanders have invented seismic base isolation. Everybody was talking the experience of seismic base isolation in New Zealand. But what we found in a building built in 17th century, look here, wood logs under the foundation. How? What are these wood logs doing under the foundation of this building built in 17th century? Why? Same thing as the modern one. Now we are putting new material in seismic base isolation in modern buildings. This because the earthquakes are coming from underground, 50, 70, 100 kilometers more. The energy is coming from down, from the soil. Then all the structure is on the foundation, which is transmitting the weight of the building and the earthquake loads. Then when the soil shakes, we have these logs, wooden logs, move under the building. In moving, they absorb energy. Then a small quantity of energy will go to the building, a small quantity. And the other quantity, bigger quantity, maybe 90%, 85% of energy released by the earthquake will be absorbed by the movement, small movement. When I say movement, it's a small movement. It's about millimeters. And to have millimeters on this, all the weight of the building, you need to absorb a lot of energy. This we found it in the seismic base isolation at the palace of the day of the governor in the citadel of Algiers. It's still there. Then we have this seismic base isolated, means we isolate the building from the soil by some techniques. Now we have a lot of modern techniques to isolate that. Then in 2010 and 2012, we had a project, European project, with 10 universities, and my university and my lab was inside this consortium of 10 universities studying just cultural heritage. And one of the case studies was the Casbah of Algiers. The other was Rhodes, another case study was in Slovenia, and France, southern France, Greece, France, Italy. Then for Algiers, when the delegation came of the universities of scientists came to a meeting to see the case studies, which I presented, to say why these case studies is very important. Then we decided to build. We said, oh, these arcs and these wooden logs are everywhere. And they said, let's try these arcs. Then we rebuilt the Algerian arc from the Casbah in our laboratories in Rome, in Italy, on a shaking table. You can see here the shaking table. This is the shaking table here. And we built it. We built two arcs, one with woods, another one without woods. And we increased the acceleration as an earthquake. We increased slowly, slowly, slowly to see at what extent the arches with and without woodlogs will resist. The first one who failed is the arch without woodlogs. The second resisted more. And see, we can see here the one without, down here on the checking table, creating earthquakes without woods. Then we said, before that, in Algiers, we made an experience with the walls, with the woods. And here we made the arcs. Then we had the experience and we concluded that the arcs, the woodlogs in the arcs are really earthquake-resistant techniques. And this is what I have to say. I hope you liked it, my visit to the Casbah of Algiers, and I hope someday you will come to Algiers and we go together visiting the Casbah. Thank you very much for your attention. Thank you.